Right, so I want to do an example problem with using the method of virtual work to solve a mechanism problem, compliant mechanism problem. So just a simple one here. I've got a double slider mechanism with compliant short length flexural pivots connecting to a central link. So the first thing I'm going to do is I'm going to turn that into its pseudorigid body model. And I'm just going to have torsional spring there. Going to have another slider over here with its pivot like that. And this one will also have a torsional spring. And so I've got a K1 right there and a K2. K1 is just going to be EI1 over L1, where L is the length of that short length flexural pivot, and I1 is the area moment for that second moment of area for that the cross section of the beam back there. And I've got going to have a similar sort of equation for the torsional stiffness of this other joint right here. Now, what I'm going to find is that in order to model this, I'll need a vector loop, and I'll have, let's call it R1 right here, R2 right there, and R3. And because we've got our input force acting right here, when it moves, it's going to change the length of R2. And so this is a 1 degree of freedom mechanism. And so what we're going to find is that we need one input. And so our generalized coordinate, this is just going to be our independent variable. Our generalized coordinate, I'm just going to pick that as R2. Okay. And so we can write our vector loop equations. We'll just have R2 equals R1 plus R3. And so that'll give us position equations that will look like R2 cosine theta 2 equals R1 cosine theta 1 plus R3 cosine theta 3. And of course, the y direction is going to be R2 sine theta 2 equals R1 sine theta 1 plus R3 sine theta 3. All right. Now, what we'll also have for this is we'll have a virtual work equation. And so our virtual work will have the work done by the force. And so that's just we're going to have F dot dr2. Okay, so that's the work done by this force. That's going to have to be, okay, sorry, let's just add everything up. Plus, and we've got two sources of potential energy here. We're going to have minus dV dr2 dr2 for the first spring, and then similarly for the second spring. I'll just write it like this for now. Okay, and so I need an expression for that V1, for the potential energy associated with that spring. And well, V1 is just going to be K1 over 2 times, it's just going to be, we'll just need that, the change in angle associated with that link. Okay, and so that's going to be associated with theta 3. And so as theta 3 rotates, that spring is going to change. And so we'll call that a theta 3 minus theta 3 naught squared. And so then we'll also have for V2, that one will have K2 over 2, and it'll be theta 3 minus theta 3. And this would probably be a different angle here, so we'll call it theta 3 naught 2 right there. So whatever the initial angles are for those. And so those will probably be complementary angles, this theta 3 and that theta 3 naught, for your starting position, because it's going to be associated with that angle and that angle, and how they change from those positions. But the change is going to be associated with theta 3. Okay, so what we're going to need in order to find what this term dv dr2 looks like is we're going to have to take the partial derivative of v1 with respect to r2. And so what we find is that's going to give us, we'll have k1 times theta 3 minus theta 3 naught, and then we'll have the derivative of this with respect to r2, and so we'll have d theta 3 dr2, and then dv2 we're going to have is just going to be equal to k2 times theta 3 minus theta 3 naught 2 times d theta 3 dr2. Okay, and so what we see is that we need an expression for d theta 3 dr2 in order to figure out what's going on here. And so the easiest way to get, that's the kinematic coefficient. And so we just need to derive the kinematic coefficient, and we can get that. We can go back to our governing equation. Kinematic coefficients are always related to the position vector loops. And so if we look at this loop and we see that theta 3 changes and R1 and R2 change, and we're interested in the relationship between theta 3 and R2. And since R2 is our independent variable, we're going to take the derivative of that function with respect to R2, and we'll get dr2 e to the I theta 2 equals dr1 dr2 e to the I theta 1 plus r3 d theta 3 dr2 I e to the I theta 3. Now this is the quantity we want. This is also unknown, but we don't necessarily care about that right now. And this right here, it's just going to be 1. Okay, that's just, how does R2 change with R2? Well, they're equal to each other, so it's just going to be 1 no matter what. And so we get this equation that we're going to be looking at, e to the I theta 2 equals dr1 dr2 e to the I theta 1 plus r3 d theta 3 dr2 I e to the I theta 3. We've got this unknown right here that we just want to get rid of because we want to solve for this, get an expression for d theta 3 d theta dr2. Okay, and so we're going to make this term pure real by multiplying through the equation by e to the minus I theta 1. And so we'll get e to the I theta 2 minus theta 1 equals dr1 dr2 plus r3 d theta 3 dr2 and then I e to the I theta 3 minus theta 1. Now, we can get rid of this term by taking the imaginary part, and that will give us just sine theta 2 minus theta 1 equals, this will become 0, and then we'll have r3 d theta 3 dr2, and then we've got I e to the I. When we take the imaginary part, that'll just be cosine of theta 3 minus theta 1. And so we can just isolate the d theta 3 dr2, and that will give us d theta 3 dr2, should just be a regular d, is equal to sine theta 2 minus theta 1 divided by r3 cosine theta 3 minus theta 1. Okay, and so we can now go back and plug in d theta 3 dr2 into those two equations. And so we'll have dv1 dr2 is just k1 theta 3 minus theta 3 naught. And then we'll have a sine theta 2 minus theta 1 over r3 cosine theta 3 minus theta 1. And then similarly for the partial of the potential energy, how the potential energy changes when R2 is moved, we can get expression now for that by just plugging in to this expression for dV/dr2. The only thing we've learned what the d theta 3 dr2 is, and so we're going to have k2 theta 3 minus theta 3 naught sine theta 2 minus theta 1 over r3 cosine theta 3 minus theta 1. And so now we've got expressions for those things, and those are the terms that go here, and that's going to be equal to 0, and this is our virtual work equation, our energy balance. And so we will have F dot dr2, and then we'll have minus this whole term, which will be k1 theta 3 minus theta 3 naught sine theta 2 minus theta 1 over r3 cosine theta 3 minus theta 1. And then we'll have minus k2 theta 3 minus theta 3 naught 2 times the same sort of term, sine theta 2 minus theta 1 over r3 cosine theta 3 minus theta 1. And so what this is going to look like is we're going to have just F equals, so this is going to have a dr2 term and a dr2, and all that's equal to 0. And so the dr2 term can go away, can be kind of factored out of the equation or divided out of the equation, and we'll just have, and then we can bring the F to the other side, and we'll have F equals k1 theta 3 minus theta 3 naught plus k2 theta 3 minus theta 3 naught 2, and all that's multiplied by sine theta 2 minus theta 1, all divided by r3 cosine theta 3 minus theta 1. And that'll be our expression for force.